So this is just going to be a discussion about Kirchhoff's rules and how to solve the example 19.8 from the book Giancoli 6th edition. So what is the story about Kirchhoff's rules? When you have a complicated circuit, such as this circuit that you see here on the left side, instead of using just the idea of trying to find the equivalent resistance, no, using circuit in parallel, circuit in series, trying to get the equivalent resistance, and then just go for this equation, V equals to Ri, either to find the current or to find the potential, the voltage. Instead of going for that, as we've been doing throughout chapter 19, if the circuit is too complicated, as you see here you have two batteries that you cannot simplify just by using equivalent of resistance, we will have to resort to Kirchhoff's rules. And what are these rules? The first one, the first Kirchhoff's rule or junction rule says, let's read it here, the sum of currents entering a junction equals the sum of the currents leaving it. And so, as we said, the currents, the charges are conserved, they don't disappear, they are not created from nothing. So, if it is conserved, whenever we reach a junction, the sums will have to be equal. So, let's pick this example of this drawing here. You see, we have here I3 going from point B to A. We have this current I3. Once we get to this point A, this is a junction. You see that the current splits into I1 and I2. So what this rule is saying is quite trivial. It is saying that what we would have to write is that I3 is equal to I1 plus I2. So this would be a use of this first rule. Okay, now let's have a look at the second rule. The second rule says the following. The sum of the changes in potential around a closed loop is zero. So again, if I look at this complicated circuit, what is a loop? It's any point that I pick and I come back to itself. So for example, if I start here at A, I go from A to H to D to C to B and come back to A, this is a loop. Okay, but there are many different loops that we can think of. I could think of this big loop where I go from A to H to D to E to F to G and back to A. This is another loop. Okay? Anyway, any loop that I pick like that, if I sum the potential for each part all around back to the point where I started, I have to make this sum equal to 0. To understand this better, let's pick an easier circuit that we are more familiar with, which is the circuit here on the right side. Okay, so if I had to solve this problem, I would use the old methods that we've been using, right? I would say this voltage here, this potential difference 12 is equal to this resistance 400 multiplied by I plus 290 multiplied by I, and then I would solve this problem. Let's say I would find the current in this from this equation. So what I'm using here is a circuit in series. I could even have written the equivalent resistance if I wanted. So this is the way we would solve. But if I wanted to solve the same problem using Kirchhoff's rules, what would I do? I would do the following. I would start, let's say, at point A. Well, let's start at point E to try to follow this graph that is at the bottom. So let's start at point E. As I go from E to A, nothing has changed. So I can say that the potential, not the potential difference, but that the potential at point E and the potential at point A is the same. Okay. Now when I go from A to B, I pass through a resistance, and so I have a drop in the potential. Okay, so the potential at point B is smaller than the potential at point A. So what they are trying to give you, that they are trying to tell you here with this plot at the bottom, is trying to make an analogy that every time we go through a resistance, the potential drop. So they're trying to make an analogy with like a roller coaster. So suppose here you're in this roller coaster. Now, so you go from point E to point A, nothing has changed because your height is all the same in this roller coaster, so the potential is the same. Same thing here in your circuit as you go from E to A. Okay, but as we go from A to B, it's as if we had having gone on the slope of the roller coaster. Now I go here from A to B, okay, because I lose potential. And then as I go from B to C, again, I see a resistance. So if I'm making this parallel with the roller coaster, again, I went through this slope from B to C, lost potential. As I go from C to D, nothing happens. So it's as if I was going in a straight line, the same height everywhere. And then from D to E, I pass through the battery. So the battery gives me potential. So then I go back to the top. Okay, so this was a loop. I went from E, A, B, C, D, back to E. And I use this analogy with the roller coaster, that every time I go through a resistance, my potential drops. And once I go through the battery, I regain that potential. So how would I write this mathematically now? Okay, so I'm going to start from E, and we said the E and A are equivalent, so no big deal. But as I go from A to B, as we said, the potential in B is smaller than the potential in A, so I know that this is a negative number. So I'm going to write this VB minus VA as minus, no, because it's negative, 400, which is the resistance, multiplied by the current. Okay, so this is my drop in potential. Now I go from B to C, again another drop in potential, because VC minus VB is again a negative number. So I'm going to write this as minus 290I. Okay. I go from C to D, nothing special. As I go from D to E, I go through the battery, so I'm going to win potential, and I'm going to write this plus V. Okay. And now, once I cross to D, I'm back to my initial point E, so this is 0. Okay, so look at this equation. This equation is pretty much the same that we had written up here. Okay? I just put everything on the left side, and that's why these terms here became negative once I put on the left side. Okay, but it's the same equation. But one way, how we are writing this equation, we are going through point by point, dropping the potential. So then I put this negative sign here every time I go through a resistance. And once I go through the battery, I gain that potential back. And so we gain the potential back when I go from small to large potential. So this is the battery. So as I go from small to large potential, I gain my potential back. And every time I'm following the current, and I see a resistance, then my potential goes down, and this is what we are seeing here. Okay, all right, so we understood that. Now let's come back to our complicated circuit, and let's try to find these currents. Okay, so we are going now to the problem that it's in the book. This is the problem 19.7, and let's see how we are going to solve it. Okay, so I'm going to erase all this that we wrote, and let's see. First thing that you do when you see a circuit like that is to put the currents. In this drawing, when you're lucky, they already did the job for us, but if these currents I3, I1, I2 were not written there, you would write it yourself. And then you may ask, but in which direction should I put this current? How do I know the direction? It doesn't matter. You choose any direction you want, and then at the end, you will see if you guessed it right or wrong. If you guessed it right, the answer for your current will be positive. If you guessed it wrong, you will get a negative number for your current. And then you will just know that, well, I guessed the wrong direction. Okay? All right, so let's use the two rules from Kirchhoff's, the two Kirchhoff's rules. The first one we already talked about is the junction, that the sum of all the currents at the junction, the sum of the currents at the junction should equal that at any junction, the sum of all the currents entering should be equal to the sum of all the currents leaving. All right, so this one we already wrote. Let's write it again here. I3 has to be equal to I1 plus I2. So I'm picking that junction at point A. All right, so you see that we have here 3 unknowns. So just one equation, of course, is not enough. We need 3 equations to solve. 3 equations to find I1, I2, and I3. So let's go for the second rule, which is let's pick loops. So one loop that the book chooses is this one. We start at point A, go to H, D, C, B, back to A. Okay, so how would we write the equation for this loop? So from A to H, you see we are following the current. So every time we are following the current, every time we see a resistance, we have a drop in the potential. So I'm going to write here minus 30 I1. Very good. So I'm now in point H. From H to D, nothing happens. There is just a wire. The wire has negligible resistance, so we don't do anything. Now I go from D to C, and you see that I'm going from low potential to high potential, right? So I'm crossing the battery. I'm getting a potential. I'm going to put here plus 45. As we go now from C to B, we are following the current I3. We are following the direction of the current I3. As we go from C to B, a drop in potential, so I'm going to write here minus R. This little resistance here is 1. Okay, so 1 multiplied by the current that I have now on this wire, which is I3. And now from B, I'm now in point B. To go back to A and close the loop, again I'm following the current. I'm going through a resistance, so I have minus 40 I3 equals to 0. All right, so I'm done. So I have here one equation. Here I have a second equation. I need one more. So I'm going to look for another loop. What the book chose, the other loop that the book chose is A, H, so it starts similar, A, H, D, but then we keep going down. D to E to F, G, back to A. Okay, so let's pick this other loop here, and let's try to write the equation. Remember, as we are following the current, every time we pass through a resistance, the potential drops. Okay, so I go from A to H. We already did this. I'm going to write here minus 30 I1. I go from H to D, nothing. As I go now from D to E, be very careful. Be very careful because as I go from D to E, I'm going opposite to the current I2. See, the current I2 is going counterclockwise, and from D to E, I'm going clockwise. I'm going opposite to the current I2. So if I'm going opposite, as I pass through the resistance, my potential actually grows. It actually increases, okay, because I'm going against the current. My potential drops only when I go together with the current. Here I'm going against the current. So here I'm going to put plus 20, which is the resistance I2. All right, so this is a point where people usually make mistake. Again, now I'm going at point E to F. I'm going against the current. So I see the resistance. I'm going to gain potential because I'm going against the current. So I have here plus 1, which is the resistance I2. All right, and then finally, I'm going through now the battery. But what I'm doing here, I'm going from high potential to low potential. You see? So what is happening here, as I go through the battery, instead of gaining potential, I'm going to lose because I'm going from high to low potential. So I'm going to lose. And then I'm back. I'm here at point G. G and A is the same thing. So I'm back and my loop is closed. So this is 0. Okay. So now we have those 3 equations that we needed. And now it's just a matter of solving equations. Okay. The idea, a good idea how to proceed is here, this equation here depends only on I1 and I3. So a good idea is to isolate I3. How can I isolate I3? Well, you can work a little bit on this, and then you can double check that I3 will be equal to 1.1 minus 0.73 I1. Okay? The other one, you can again work a little bit on it and isolate, because here you have just I2 and I1. So you can isolate I2. You will see that I2 is equal to 3.8 plus 1.4 I1. What you're going to do now? Well, you pick this I3, put it here. You pick this I2, put it here, and you're going to find I1. Okay, so you're going to find I1. You will see that I1, once you use everything in this equation here, you will see that I1 is equal to minus 0.87 amps, and this is a very good result. Let's stop here a little bit. What is this telling us? Well, it's telling us that the direction that the book chose for the current I1 is actually not the correct one. See, so the current is actually not going from A to H, but is actually going from H to A. Okay, so the current I1 doesn't go like this. It actually goes from D to H to A. All right, so that's what I told you. Even if you choose the wrong direction of the current, well, you will find it out at the end when you get the numbers. Okay, once you have I1, so you come here to this equation to get I3. You're going to find out that I3 is equal to 1.7 amps. So this one is in the correct direction. You come back to this equation here with I2, and you're going to find that I2, using the value for I1, you're going to find that I2 is 2.6 amps. So this is the end of this example.